The first experiment we'll be doing in the course with the Sphero mini sensor board. It's a Slingshot Sled Kinematics experiment. It simply involves position, velocity, and acceleration. You use the Sphero mini sensor board to measure the acceleration as a function of time, and then this Mathematica document that you're looking at on the screen now integrates the acceleration to get the velocity, and then integrates the velocity to get the position. So, here's the theory that underlies this experiment. You're going to use the Sphero sensor board to measure the acceleration as a function of time. If you know acceleration as a function of time, that's the time derivative of v with respect to t, dv dt. So I take this equation here and integrate it. I get velocity at time t equals the previous velocity at time 0 as the integral from 0 to t of a Sphero as a function of tau integrated d tau. Once I know that, I can use the position, I can get the position as a function of time from the velocity by one more integration. So we simply take the finite difference of those derivatives using these trapezoidal law results from elementary calculus. Those two velocity and acceleration formulas look like this as a Mathematica do loop in the program. You don't need to understand how to use Mathematica to use this. I'm hoping that some of you may get so interested in Mathematica that you want to dig into it. You can see all of the procedures in the Mathematica file. So here's the experimental procedure. I'll show you how to build the sled that you'll use to take the data. What we're going to do is take an elastic, a piece of elastic, stretch it between a support structure down here and some initial starting point. This elastic is in tension. It's a spring, but the spring is an elastic, so it is a spring in tension, but it cannot support a force in compression, so it's not an ordinary spring. It's a springy. Okay, so this document here you can read and figure out where you want to do the experiment. I talk about that in the setup video as well. Okay, so we start from here. We let go of the sled. The sled starts to accelerate in this direction because of the spring tension in the line here. It has an increasing acceleration up until the point where the spring string relaxes to its unstretched length L0. Okay. After this point, the spring is no longer a spring, it's just hanging there in the breeze, and the particle continues to slide forward until it comes to a stop. Okay. So there's acceleration from here to here and deceleration between here and here. There's deceleration due to friction all along the way. At this point, that force is only frictional force. Okay, so we want to measure the stopping distance. We'll get predictions for the position as a function of time and velocity as a function of time, and you'll see how that compares with what you measure on the floor where you're taking this data. This procedure will be talked about in the video part. Read this in conjunction with watching that video, and then we analyze the data shown here. Here's how you build the sled. Start by tying the end of the string, the elastic, into the hole in the sled ruler bottom. This stuff is kind of hard to handle. Tie a couple of 3 or 4 knots and then take the piece that's left over and tape it down to the back here. You don't want to get that string underneath the surface here, and you don't want to get any tape on the bottom part of the plastic. That's the nice, smooth, frictionless, low friction surface that we want. Take that there, and then take a little chunk of 1/4 of a Kleenex tissue, fold it in half again, and then kind of one more time in half, and stuff that into the bottom. Take the SMSB and put it with the battery side sticking up in the bottom of the plastic cup. Take that Kleenex spacer and put it there.
put the lid on tight. The Kleenex kind of keeps it from rattling around, and this way you can see the LED light when it's connected. It'll be facing up. Now, here's the most crucial thing, the only thing you can really go wrong. You want to line this up. Here's the USB port, so the positive y-axis accelerometer points that way. You want to mount that on the slide so that the string, the forward direction pulling by the spring, the springy string, lines up like this way. So you want the positive acceleration that way. So you want the USB port sitting there. So take a piece of Scotch tape and tape this to the plastic, and the tape sticks to itself. So stick it here. And again, you want to make sure that the tape doesn't get onto the bottom of the sled. Try and line it very carefully. That looks pretty well up. And roughly in the center of the ruler, it's not crucial. Wrap this down tight so that you push that down there. That one's not long enough, so tape it more pieces of Scotch tape than you might think you want to do. You don't want this thing to rattle around on the sled. So a couple more pieces here, and now it's good and tight on there. And take a number of quarters. I, just for arbitrary reasons, kind of roughly optimized, I happen to choose 7 quarters, okay? So $1.75 worth of quarters. And they want to get taped to the back of the sled. So you can put them back here like this. Again, nothing terribly crucial. Put it there and you can tape to the bottom there. Don't wrap the tape around the bottom of the plastic ruler. So tape it here and here. Another, that's 3, that's 2 more, that's 5. That's 5, and a piece of tape here, piece of tape here. You're starting to obscure the USB port, but I can still see it there, okay? And the last 2 there, so that's 7 quarters of mass ballast that we want this thing to have. There, like that. And there's the ready-to-go sled. Beautiful, huh? Not like the rocket sleds of the NASA program, but there's the sled. The string is pulling this way, the USB port is pointing back that way, going this way, and we're ready to go. Here's a convenient way to attach the spring down, the string spring down here. Leave it on the little tab. Put it inside the binding of a hardcover book. Stack a bunch of other books, heavy books on top of it, and then that's the end point of the spring down here. We choose the origin actually down there at the starting point, but we measure all the distances from this datum plane here. So the first thing you want to do is measure the unstretched length of the spring. So pull the sled back until you can't see it in the video probably, but here the spring is just starting to get under tension. So I want to measure that distance here from the book, from where the spring starts. So that's 2.32 meters, 2.32 meters. Okay. So then all you do is start there, start pulling this back, and pull it back. It doesn't go very far. Pull it back some more, goes further. This little piece of paper marks the 3-meter mark. That's the length of your ruler, so if you have distances longer than that, and hopefully you will, you can measure 3 meters to there and go back from there. So about here, we will see the sled make it almost all the way to the end point. Ooh, perfect, just there, so I'm gonna remember that and start from here. Okay, so now we're recording on both devices. So we go. We're going to take some data now, so I go to My Programs, go here, Start, Create. I'm going to push Start. It'll find the robot. It's this one here. The robot's light should light up. It's ready to go there. Okay. So I'm going to pull this back now. pull this back to where I thought was a good starting point. I've got my starting point here. And now I'm ready to let go. I push the start on the recording button, and I wait at least 2 or 3 seconds to get some baseline data for the accelerometer 0. So I'm going to push start, and I can scroll ahead to the accelerometer thing. I've gone more than 2 or 3 seconds. I'm going to let go. And then as soon as I do that, there's the data. So I'm going to stop now. I'm going to stop. Now we've got all the data. And there's 2 things we can do. We can look at the raw data, which is the sensor data here. Okay, location, garbage. There's the gyroscope. Here's the accelerometer data that we want. So I'm going to show that. And I can scroll here. So this purple one, I'll get rid of the green. I'll get rid of the Z. And I'll get rid of the total. All we want really is the y-axis data. So there's the acceleration up, positive acceleration, negative acceleration while it's slowing down. I'd like to capture 2 things. I'd like to do a screen grab of this data, even though the data set will reproduce it. But let's do a screen grab. So I'm going to mail it to myself by pushing that button there. And I'm going to mail it to myself, me, John, or Conrad, at me, and I'm going to call this one run 1, okay? The other thing you can do is put the numbers that you measured for the spring length and the starting distance. I want to measure the stopping distance here, okay? So, but I'm just going to call this run 1 to save time here. Run 1, and I'm going to save that. That'll save that screen grab. But please don't stop there, because what you really need to grab is the raw data for the Excel spreadsheet data set, okay? So I go back to here now, and I close this X here, and I pull all the way back to the top again, and I push the button that says download CSV data. All I want is the accelerometer data, which is that one there. I email it to myself again, and me again. There's me, and this is, I should have called that previous one run 1 screen grab, but this one I'm going to call run 1 Excel data. And you see it puts, there's the Excel file there. It's a comma separated variable file. I'm going to email that to myself. There's that. Oh, I did that again. And that's it. That's all you need to get the data. Now I'll show you how to analyze that data with your Mathematica template.
Now I'm going to show you how to analyze the data. You want to take the CSV file that we just captured. That's this run here, run 1. And we're going to drag it into this place here between the Excel data equals, this blank space, and that there. And we do that, and we hit a carriage return here, shift and enter, enters that into the program. And then come down to here, to step 3, move the cursor at the end of this line, step 3, hit shift enter again, and that generates the data file then that you saw in the video. Here's the acceleration as a function of time. Here the spring is accelerating the sled, and at this point here the tension in the elastic went to 0, and it's just the deceleration due to the friction. This is the first curve. It's in units of g, so 0.6 g is the peak acceleration. The Mathematica file does 2 things. It converts that g to meters per second squared. That's just a simple mathematical multiplication. But also notice that there's a little shift offset up here. Mathematica samples the first 2 seconds and says during that time the acceleration should average to 0. So it does a little calibration offset down here, so the acceleration there is like that. Okay, so there's acceleration as a function of time. The last step then is to analyze that data by coming down here to put the cursor at the end of this section here. In step 4, you put the cursor here, do shift and enter, and then it gives you velocity as a function of time and position as a function of time. Okay, and you can actually pick data values off of this curve here. See, the velocity peaks at about 2.5 meters per second here, and you can see where the position stops at about 4 meters, like that. Okay, there's a little bit of an artifact down here. I don't know what that's all about. So I didn't cheat. Okay, but you can pick those values then off of this table. So here's the peak distance after about about 8 seconds. The distance, this column here is the position. So it went a total distance of about 3.9 meters. That's pretty close to what you measured on the floor there, it seems like. And so that's how this works. I'll show you in the Moodle instructions later on in the course how I want you to keep track of that data and process it.
Here's how you can make a drogue chute to get some more drag in the problem. Large styrofoam cup, loop of string. You can tape something to, you can just tape this string to the back of the sled if you want to, but it's kind of convenient to tape a paper clip there so that you can move it on and off of the clip. So that'll give you nice drag, controllable drag. And you can launch it by holding onto the drag chute. That'll be a nice clean way to let go as well. So this is without the drogue chute. Almost made it to the end. So this is with the drogue chute. This is like run 6 and run 7.
Here is a simulation that you may or may not use in a later lab. It's an integration of the dynamics, uses the integration of Newton's laws for the spring mass system with the configuration here shown here. You can see the initial acceleration, the falling down here. Here's the position. Here's the velocity as a function of time, and here's the position as a function of time. You can pause this here and pull down the graphics menu, drawing tools, and you can actually pull off which one of these is it now? Oh yes, pull this one here. You can pull this one here, and you can pull that one and actually pick data points off the curve here. Here's the peak velocity at 1.1 second, 2.4 meters per second, and you can pull these that off. I may show you how to do that in a later part of the course.